Welcome to the Deep Dive. You're here because you want to get smart, fast, on some really interesting topics.
And today we've got a paper that's, well, pretty fascinating. It digs into how computers play chess.
Yes, specifically looking at how they sort of represent the board and learn to play at that crazy superhuman level.
If you're into machine learning, this is some cool nuts and bolts stuff.
It really is. The paper kind of hits two main things. First, this really elegant engineering for understanding the board and finding moves fast using something called rotated bitboards.
Okay, intriguing.
And the second?
The second part is the journey of reinforcement learning in chess, how we got to things like AlphaZero and maybe how we can make that learning more efficient, faster.
Got it. So it's not just about chess, right? This efficiency idea applies more broadly in AI.
Absolutely. Sample efficiency is a huge deal everywhere, but let's start with those rotated bitboards. Sounds technical, but the core idea is clever.
Lay it on us. Bitboards first, I guess.
Right. So think of the 64 squares on a chessboard. A bitboard uses a 64-bit computer word, just a string of ones and zeros to map things out.
Like one bitboard shows where all the white pawns are, maybe.
Exactly. Or all occupied squares, or just the black pieces. You can have several different bitboards representing the state.
And the advantage is speed.
Totally. Computers are brilliant at manipulating these blocks of bits all at once, parallel processing, basically. So checking things across the whole board becomes, well, much faster.
The paper mentions this isn't brand new, right? Engines like Chessafor 4.5, Cray Blitz, they use this.
Yeah, the concept's been around. Bitboards were a key innovation for making engines faster back in the day. Essential, really.
Okay, so we have these maps of the board. How does that translate into figuring out possible moves? That seems like the next step.
It is, and for some pieces, it's fairly straightforward. Knights, kings, their moves are always the same pattern from a given square.
Right, a knight always moves in that L shape.
Exactly. So you can just pre-calculate all possible knight moves from every square and stick them in a lookup table. Super fast.
But the sliding pieces, rooks, bishops, queens, they're the tricky ones.
That's the challenge. A rook's move depends entirely on whether other pieces are blocking its path along a rank or file. Same for bishops on diagonals.
Okay, so how do bitboards help there? That's where the rotated bit comes in, I bet.
You got it. This is the really clever part detailed in the paper, especially in the FUSc Shag engine they discuss. They don't just have the standard board representation.
They have twisted versions.
Kind of. They maintain versions rotated 90 degrees and also along the two main diagonals. Imagine turning the board.
Huh. Why do that?
The magic is these rotations line up the squares along a file or a diagonal into a nice contiguous block of bits within that 64-bit word.
Ah, I think I see. So instead of jumping around the 8x8 grid to check if a rook's path is clear,
you just look at a specific chunk of bits in the right rotated board. It makes figuring out the occupancy along that line incredibly efficient.
That is clever. Does the paper show how it works in code?
It does, yeah. It gives some C# snippets from FUSc Shard. For simple pawn pushes forward, it's just bit shifts, moving the bits representing pawns one step forward, and then checking against the empty squares bitboard to make sure the destination is free.
Paint capture.
Similar idea. Shift the pawn bits diagonally, then check against the opponent's piece bitboard. They also handle, making sure pawns don't capture off the edge of the board. Standard stuff, but done efficiently with bits.
What about the sliders? Rooks.
Okay, so for a rook, you'd grab the occupancy pattern for its rank from the normal bitboard. Then you'd grab the pattern for its file from the 90-degree rotated bitboard.
And use those patterns.
How? You use those patterns, often just a byte representing the 8 squares on that line, as an index into pre-computed tables. These tables tell you exactly which squares the rook can move to from its current position, given that specific blockage pattern.
Wow, okay. Pre-calculation doing heavy lifting again.
Exactly. The paper mentions they even use byte-level access and need functions to convert square indices between the normal and rotated views, like L90 to normal. It's quite optimized.
And bishops are similar, but using the diagonal rotations.
Yep. Using board.ok1h8 and board.ok8h1 to get the diagonal patterns, then indexing into tables like 018 moves. And the queen, well, she's just a rook and a bishop combined move-wise.
So you just run the rook logic and the bishop logic. Makes sense. But how do you know this incredibly complex move generation logic is actually correct? No dugs.
Good question. That's where something called perft comes in. Performance test, basically.
Okay, what does it do?
You give it a position and a depth, say depth 5. It then explores every single legal move sequence down to that depth and counts the total number of leaf nodes the final board positions reach.
This is like a brute force count of possibilities.
Pretty much. And there are standard chess positions with known verified perfed counts. So you run your engine's perfed on these positions, and if your numbers match the known values.
You can be pretty confident your move generator isn't missing moves or making illegal ones.
Exactly. It's a crucial validation step. The paper shows FUSC Sharp's perfed results for the start position, a tricky middle game, and an end game.
And they matched Crafty, another well-known engine.
They did, which is great validation for FUSC Sharp's move logic correctness.
Correct you is faster.
Yeah, the paper notes Crafty crunched more nodes per second. They suggest it's likely down to Crafty being written in highly optimized C versus FUSC Sharp using C#.net, which can have a bit more overhead. Plus, Crafty's had decades of tuning.
Right. Language choice and optimization effort matter.
Yeah.
Okay, that covers the board representation and move generation pretty well. Let's shift to the second major part. Reinforcement learning.
Right. The paper gives some history, starting around 2008. Back then, reinforcement learning in chess was often about tuning the evaluation function.
That's the part of the engine that guesses how good a position is, right?
Yeah.
Like +1 for a pawn advantage or something.
Sort of, yeah. But much more complex. Engines had lots of handcrafted features: king safety, pawn structure, piece mobility. RL was used to automatically tweak the weights of these features by having the engine play itself, using techniques like temporal difference learning.
Did it work well?
It helped, for sure. The paper mentions NeuroChess2, an earlier neural network attempt, but it struggled a bit, especially with pure self-play. It wasn't quite there yet.
Which sets the stage for AlphaZero, that 2017 paper. Really shook things up.
Oh, absolutely. DeepMind's AlphaZero was revolutionary. It showed you could take a general RL algorithm, feed it only the rules of chess, nothing else, no human strategy.
And it learns to play better than any human or previous engine just by playing itself.
Incredibly fast, too, like superhuman chess in under 24 hours. Same algorithm also mastered Go and Shogi. It was a landmark moment.
And his whole approach was different from engines like Stockfish, right? Stockfish does this incredibly deep search.
Exactly. Stockfish uses alpha-beta search, looking many, many moves ahead, evaluating millions, even billions of positions per second. AlphaZero used Monte Carlo tree search, or MCTS.
MCTS, that's different how?
It still searches, but it's guided by a deep neural network. AlphaZero actually evaluated far fewer positions per second than Stockfish.
So how did it win?
Its neural network was much better at judging positions and figuring out which branches of the search tree were actually promising. It was a more selective search, more intuitive, almost human-like in its focus. Quality over just quantity.
And it even rediscovered standard human openings.
Yeah.
Without being taught them.
Yeah. Which is pretty amazing validation. It learned the value of controlling the center, king safety, all that stuff from scratch.
But there's a catch, isn't there? The paper mentions the amount of training.
Right. Sample efficiency. AlphaZero needed millions of games of self-play, like 44 million games over those hours to convincingly beat Stockfish. That's a colossal amount of computation.
Which brings us to the FUSC Shag Zero idea in this paper. They're thinking about how to do better.
Exactly. The authors propose using FUSC Shag's existing bitboard structure, which already captures chess concepts efficiently, as a kind of built-in language for the learning system, a domain-specific language, or DSL.
So instead of the neural network learning everything from raw pixels or a simple board state, it starts with these more meaningful bitboard features.
That's the core idea. The hope is that by giving the RL system this structured knowledge, like bitboards representing rook attacks on open files or passed pawns, it might learn strong evaluation heuristics much faster.
More sample efficient, needing fewer games than AlphaZero's more blank slate approach.
Precisely. Maybe it could rediscover those key chess principles with less brute force self-play. They suggest maybe using something like Leela Chess Zero, LC0, another strong open source engine inspired by AlphaZero as a sparring partner.
And potentially tailoring the learning based on the game phase, like opening versus endgame.
Yeah, classifying positions could help focus the learning too. It connects back to their own earlier RL work from 2008, which they note was actually more sample efficient even if it didn't reach AlphaZero's peak strength.
So they're proposing concrete steps. Building this FUSC Shag Zero.
Seems like it. Getting the engines running together, designing the learning setup, creating that bitboard DSL, maybe incrementally. It's a research direction.
And this whole AlphaZero approach, it's gone way beyond games now, hasn't it?
Oh, massively. The paper touches on this. Think AlphaFold for protein structure prediction, huge implications for biology and medicine. Nobel Prize recognized work came from it.
Right, I've heard of that.
Then there's AlphaTensor, finding new, faster ways to do fundamental math operations like matrix multiplication, and even things like AlphaProof and AlphaGeometry tackling complex math competition problems.
So the core RL ideas are incredibly powerful in general.
Definitely. And the paper even pushes into more societal applications. They mention projects looking at using AI and RL for things like ecological economic planning.
Planning economies. That sounds ambitious.
It is. They reference a specific project on critical mathematical economics and progressive computer science and discuss this idea of a strategic triangle.
Okay, what's that?
It's framed as protesting harmful uses of AI under capitalism, mitigating the negative consequences, and actively using AI tools to help design or transition towards a different post-capitalist system, like using AI for managing resources in a circular economy, maybe leveraging things like the EU's digital product passport data.
So using a tech for potentially radical change while being critical of its current uses, the paper mentions the problem with AI is the problem with capitalism.
Yeah, it brings in that political economic critique, suggesting the way AI is developed and deployed is shaped by the system it exists within. It also reminds us AI is broader than just large language models, referencing earlier work on planning.
Interesting. So even the hype around current AI might, ironically, help convince people that complex planning, maybe for a different economic system, is actually feasible now.
That's one possible implication they raise, yes, that the demonstrated power of AI makes large-scale coordination seem more technologically possible.
Wow. Okay. That took us from bitboards to potential economic futures. This paper covered a lot of ground. So thinking about all this, what kind of new research ideas, novel notions did it spark for you?
Well, one thing that seems really interesting is pushing this FUSc Shag Zero idea further, specifically the interplay between structured knowledge and pure learning.
How so?
Imagine setting up like an adversarial training scenario. You have two FUSc Shag Zero agents learning to play chess. One agent heavily relies on a carefully designed, interpretable DSL based on bitboards, maybe even one we can inspect.
Okay, the structured agent.
Right. And the other agent uses a more standard AlphaZero-like neural network, more of a black box. They learn by playing each other.
A structured versus unstructured learner face-off. What's the research question?
Could the structured DSL-based agent somehow guide the black box agent? Maybe help it learn faster, become more sample efficient by implicitly highlighting important chess concepts through its play? Or could we even allow the DSL itself to evolve during training? Maybe the system discovers new, useful bitboard combinations we didn't think of.
So the DSL learns too?
Potentially. It gets really interesting then. You could explore that fundamental trade-off, the interpretability you get from the DSL versus the potential raw power of the less constrained neural network. How do they best work together?
That sounds like a cool experiment. Probing how knowledge representation and learning interact. What's your second notion?
Thinking about those broader applications, like the ecological planning idea, what if we took the spirit of FUSc Shag Zero, the bitboard-like DSL plus reinforcement learning, and applied it to a simplified model of resource management?
Like representing ecological states with bit patterns.
Sort of. Define key variables, biodiversity levels in different zones, pollution thresholds, available water resources, maybe not literally 64 bits, but using that structured, symbolic representation idea. Then create a DSL of basic policy actions. Setting fishing limits, investing in green tech, protecting certain areas.
Okay, a DSL for ecological action.
Yeah. Then train an RL agent using this DSL. It could learn against a simulation of the ecosystem, or maybe even interactively, perhaps in a gamified way, with actual ecologists.
Learning sustainable policies.
Exactly. The key question would be, does this structured DSL approach lead to AI-generated policies that are not only effective, but also more transparent and understandable than what you might get from a purely data-driven model? Could we use it to find resource management strategies that humans can actually grasp, trust, and implement?
Applying chess AI ideas to save the planet, potentially? That's definitely ambitious, but very relevant.
It feels like a way to bridge the gap, you know?
Right.
Take these powerful AI learning techniques and see if structuring them with domain knowledge can make them more useful for complex real-world problems, where just having a black box answer isn't enough.
Those are definitely some thought-provoking directions. A lot to chew on there. So wrapping up this deep dive, the key takeaways seem to be the surprising elegance of techniques like rotated bitboards for handling complex game states efficiently.
And the sheer power of reinforcement learning, shown by AlphaZero, to achieve superhuman results, but also the ongoing quest to make that learning more sample efficient.
Right, potentially by blending that learning power with structured domain-specific knowledge like the FUSC Shag Zero idea explores.
And these ideas clearly have legs far beyond chess, reaching into science, maybe even societal planning.
Which leaves us with a final thought. Could these hybrid AI systems, the ones that smartly combine human understandable structure with the raw learning capability of neural networks, be the key? Are they what we need to tackle the really messy, complex challenges, things needing both high performance and interpretability? Something to think about. For anyone wanting to read the paper itself, we'll put the link in the show notes. Thanks for joining us.
Yeah, thanks for tuning in.